it's Annalie. Today, I'm in Glasgow, speaking with Sheila Rowan, who works with gravitational waves and has done ever since she got her doctorate here at the University of Glasgow 15 years ago. She is now also the director of the Institute for Gravitational Research. Hi, Sheila.
Hi, Annalie.
So in my last interview with Jim Hoff, who I believe was your doctoral supervisor,
He was indeed.
he told me about the new technological developments that are going on at the university in aid of gravitational wave research. Is this one of the such developments, and could you explain a bit about it for me?
Sure, it is indeed. What we've got here is a setup which is actually a prototype of part of the instrumentation for our gravitational wave detectors.
Okay.
And what we've got here, you can see we have two big metal masses.
Yeah.
Well, the one at the bottom here in a real instrument will actually be glass, 40 kilograms of fused silica, very pure glass, that forms a mirror. And in these big laser interferometers, there's a suspended mirror like this at the ends of the arms of the interferometers. Light then goes out, hits the mirrors at the back, comes back to the middle and recombines. And by looking at the intensity of the light there, we can tell if there's been a change in the length of the arms of the interferometers, because the gravitational waves that we're searching for, actually when they pass through the Earth and they pass through the interferometer, cause the positions of these mirrors to change. They actually cause them to move. And it's those changes that we're looking for. Okay,
so something like this, to scale, we could think to find in a detector.
Yep, this is a full scale system here.
Okay. I'm not sure if we can see this, but it has very, very thin fibres connecting the two steel masses. This is glass, I do believe.
They are actually. These are fused silica fibres, again glass fibres. So in the real thing, this will be a glass mirror at the bottom.
Ah, right, yes.
There's a glass kind of prism you can just see that's very carefully attached to the side, and then welded to the tips on the horns on those prisms are fused silica fibres, which are actually pretty thin. They're a few hundred microns thick. And again, to give that some scale, your hairs, typical width of a hair is about 50 or 60 microns. Wow. So they're only a few times thicker than a hair.
Right. And you make these fibres here at the university, or? We
do. Okay. There's quite a lot of work goes into carefully choosing the size of these fibres. We make them here with a specially designed machine with a CO2 laser, a carbon dioxide laser, which has a wavelength that's absorbed by the fused silica just in the surface that heats the silica up. So we put in a rod of fused silica that's maybe a few millimeters thick, heat up the middle with the laser light, and then we pull that out into these thin fused silica fibres here.
Isn't glass extremely fragile?
Well, people tend to think it's very fragile, but it all depends how you handle it. And in fact, if we have a fibre like this one and we pull straight down on the end, the fused silica glass is actually stronger than steel.
Wow.
So people tend not to think about it that way, but in fact it's really true. And we have 40 kilograms suspended here, on these 4 silica fibres, and we can actually hit it with a hammer and it'll be quite happy.
Oh my goodness. Oh, wow. And why do you use glass as opposed to string or rope or steel even?
That's a very good question, and in some of the initial instruments it is actually steel wire that's used, and steel wire is used as a sling really to support these masses. The masses sit in that. But what we're trying to do is detect the very small motions of this mirror caused by gravitational waves. And the gravitational waves come along and they start to cause this mirror to swing slightly. And if there's anything else that causes the mirror to swing, that can look a bit like a gravitational wave signal. So we have to be very careful about how we suspend the mirror to make sure that other things don't cause the mirror to swing more than a gravitational wave does. And it's to get around a particular kind of noise in the instrument that makes the mirrors move. And it's a kind of noise source called thermal noise.
Okay.
comes about from the fact that these instruments are just at room temperature. So all the atoms and molecules making up the mirrors have some thermal energy. So the whole pendulum actually wants to move a little bit. Each atom and molecule is shaking, and it's connected to the ones round about it. So they all kind of shake a bit. And what they do, because they're all coupled together, is they actually excite what's called the pendulum mode of this mirror. So you can see the whole thing is suspended as a pendulum. So here's just one fibre.
Right.
But the whole thing will swing slightly.
Okay.
And that motion gets thermally excited. As long as all the motions at the pendulum, what's called the pendulum resonant frequency, you can see this is a natural frequency it wants to swing at. As long as what's excited is that motion, that's kind of okay. That's away from the frequencies that we want to detect gravitational waves. The gravitational waves will cause this to move at sort of higher frequencies. However, it'll only swing at this nice resonant frequency, this one frequency, if the pendulum is perfect and it doesn't have any doesn't dissipate any energy. There isn't any friction to kind of stop it moving just perfectly at this one frequency. But all materials aren't perfect. They do have some kind of friction. And so you can imagine, as this pendulum swings, if there's friction associated with that, instead of swinging nicely in this lovely smooth motion, it kind of can have some extra motion because of because of friction, because of internally the material not liking the fact that it's being sort of stressed a little bit as it swings back and forward, and that can cause noise, extra motion that happens faster than that nice smooth pendulum motion. So that can happen at frequencies where we want to look for gravitational waves. Now that's kind of an intrinsic property of the material, the amount of friction it has and internal friction. Now glass, it turns out, has a pretty low internal friction, much lower than steel. And so by using glass fibres instead of steel fibres, we can actually lower the friction and lower the noise caused by that friction at the frequencies that we want to look for gravitational waves.
How are these pendulums, how are these things affected by the external world, so to say, of the detectors? I mean, can a stamp on the ground or temperature differences, can they all affect the sensitivity?
Just by suspending it as a pendulum at all, we actually help get rid of the ground vibrations and the effect that they have on the mirror. Again, quick demonstration with my little pendulum here. This whole thing has, as we discussed, as a natural frequency at which it wants to swing. And if my hand's connected to the ground, it doesn't need to move very much before the bottom moves a lot. So that's not a frequency we want to look for gravity waves at. Again, at very low frequencies, if I move my hand slowly, because low frequency is a slow motion, the pendulum, again, it moves quite a lot. It moves just the same amount pretty much as my hand does, or as the ground would. On the other hand, if I move my hand quite quickly, I can move it a lot. But the pendulum at the bottom, so the mirror in our system here, actually moves a relatively small amount compared to the motion of my hand at the top. And so this whole thing's actually acting as a mechanical filter to filter out the ground motions. And that's why we really suspend these mirrors at the bottom to isolate them from the ground motions. We also put them in big vacuum tanks, pump out all the air, so that air currents can't push on these things and cause the mirrors to move. So there's a lot of other design that goes into making sure that there aren't external disturbances that cause the mirrors to move.
So the gravitational waves have a certain frequency that you're looking for then? They have a unique frequency, or?
Depends on what the source of the gravitational waves is. If there are different sources that would cause motions of the mass at different frequencies. So we get things like supernovae, where we've got a star, it's run out of fuel, come to the end of its life, and it suddenly explodes, and there's an enormous explosion. That happens quite quickly, and so it's quite a relatively high frequency, maybe centred about a kilohertz or so, so 1,000 hertz. That's quite fast, and it also happens over a relatively short period. So it would be like a quick bang on the mirror, and it would shake suddenly, and then stop again because it's a fast event. There are other sources of gravitational waves where, say, we have two stars that are spiraling round one another, two small compact stars that spiral in, lose energy, and then come together and collapse again and again form an enormous explosion. There, we've got something that's a bit like a chirp that would have a very distinctive signal also that we would see. So it really depends on what the source is, exactly what the frequency is that we would look for in our searches.
So as Jim told me, you work with huge amounts of people and massive collaboration. Is it motivating working in such a big group, or is it more frustrating?
It's very interesting to work in a big collaboration. I mean, we kind of work at different levels in that we've a group here in which we do experiments and work in the lab. So there's a local group of people one works with. And it's nice to be able to do things on a lab scale, but it's also nice to feel that the things that we do here in the lab really matter to a lot of people. It's a big collaboration that we work in. The bigger gravity wave collaboration we work in has more than 700 people in it.
Wow.
And they're all very motivated to make these detectors work.
Yeah. Are there younger people still getting involved into the research?
There are indeed. In fact, there are summer students working. Okay. We have summer students this summer working with us in the group. There's maybe 4 or 5. Some of them are from Glasgow. So these are undergraduate students who want to get some experience of what it's really like to do research. So we've got folks working with us there. We have quite a few PhD students also, again, who are working on this, studying aspects of this for their research. And right through to postdocs who finish their PhD but want to continue to do more research in this area. So we have the full spectrum of ages. And it's a really nice thing for them to work on, because these are the folks who are doing the hands-on work in the lab. And so a system like this, we've tested it here in Glasgow, and it's the students and postdocs who really have done the hands-on work. And they're getting the opportunity in this big collaboration to play a part that really matters.
How did you get into all this fascinating research?
Well, actually I was an undergraduate here in Glasgow, and I did a summer project with the research group here. And I was hooked from that point.
I can imagine, it's very fascinating. Thank you very much.
You're very welcome.